Hello and welcome to Mrs. Horton's classroom. This video is over lesson on the levers and pulleys lab. So I'm first going to go over the levers and then we'll get the information to do the pulleys lab as well. Okay, the first thing on our worksheet, which I will send out in an email to you along with this video, this is the alternative lab. So if you did not do the lab and you still want to do it to earn points, then you can follow this video along and walk through it with me and complete it and turn it in, and I'll grade it and give you points for it. So the point value is 30 points, not 24 points. So if you finish this, total value will be 30 points. And so data will be probably given a few extra points to even that out. Okay, so first question, it says, write the goal of the labs on levers and pulleys, or the question you tried to answer. Okay, so at the beginning of the lab, it tells us, explore how levers can change the amount of force it takes to do a job. In this virtual lab, will allow you to observe the effort required to balance a mass at different fulcrum positions. So this is one of the things that you can put in here. So you'll just type that up. Okay, so the other lab, which is the pulleys lab, let me go to that really fast. Now it'll look a little bit different in our class just because this is for my next trimester's class and I haven't manipulated it like I normally would. So it looks a little bit different if you tried to go find the pulleys, because I have combined 6.04 to 6.07 into one folder. So that's why I said it would look a little bit different. But we want to go to went to the wrong thing, sorry. I want to go to investigate to get the pulleys. Okay, here we go. So give us our information. I'm going to take that back. You'd think I'd never use this curriculum. Oh, went to the wrong spot again. Okay, investigate pulleys. And here we go. Okay, so this lab is designed to be completed in 2 days. So this is the pulley lab with the levers lab, but it shouldn't take you 2 days to do it. Just keep that in mind. So this virtual lab will allow you to calculate the mechanical advantage and efficiency of pulleys. Okay, so we can put that under question number 1. And you could even put it like number 1, and for levers, and then number 2 for pulleys. Okay. Then, which we want to answer this next question. We can get rid of this. Let me put it in blue so it's easier for you to see. Okay, so number 2, which observations, experience, or lesson materials helped you form a hypothesis? So what we want to do is talk about what our hypothesis is going to be. And I'm going to help you. I'm going to write it out, and then but we're probably going to have to come back to this question because I want to play around in the lab first. So then we'll come back to this. So let's start with the levers lab. And I will make sure and give you this link, but you'll need to be logged into the system, like into our class, in order to get the link to work. So just keep that in mind when you are trying to get your own data. Because I don't want you to use my data per se, I want you to get your own data. Okay, so here is the lab. It'll take you to a page that looks like this. When you click on this, sometimes it'll give you a window that looks like that gray thing, and sometimes you have to click on it to get it to open to this. So let's go ahead and begin the lab. Let me move this over here and this one. So these are the student guides, which are also in your lesson that we didn't use for the other lab because I went over it in class, but for this one we will use it. Okay, so it says first to open the Simple Machines Levers Virtual Lab. Click the tutorial and complete the tutorial to learn how to conduct this lab. I'm not going to go through the tutorial. When you have finished the tutorial, click the home button and reset the lab if necessary. We want to write your goal for the laboratory and a hypothesis about the relationship between levers and work on the lab report. So, and what is the theoretical relationship between the effort force and the resistance force in a balanced lever? So when necessary, convert grams to newtons. Notice that the level is a large one, so the mass of the lever needs to be considered in these calculations. To do this, first set up the lever so that the spring scale is hooked to the resistance side. Okay, so let's open up the lab. Okay, so there we go. So this is the level right here, and we can move it this way. So that's moving it to the left. This is moving it to the right. Okay, so we're going to do what it tells us to do with regards to this. Now, we also have a spring scale. This is our spring scale. And when you see it cupped, that means you can pick it up. You see that? You have your hand over it like that. You can pick it up. And we'll be hanging it here or picking it up and pulling up on it. So, and it can be a little tricky with when you put your hand over it. Okay, so it says notice that the level is a large one, so that the mass of the lever needs to be considered in these calculations. To do this, first set up the lever so that the spring scale is hooked to the resistance side. Okay, so this is, this is the resistance side right here. So they want it to be hooked there. Okay, set the fulcrum at 10 centimeters on the resistance side. So 10 centimeters, like that. Place no mass on the effort side. So this other side over here is the effort side. Notice that the lever tips to the left. Pull on the spring scale and balance the lever. Fill out the table below for 3 more positions of the lever on the resistance side. Okay, so force applied to balance the lever with no mass on effort side. So that's what we need to figure out. Force applied to balance the lever with no mass on the effort side. Okay, so you're going to want to write that down on a piece of paper because this particular page I cannot type on. But we can go to this page right here. Okay, so this is to help us form a hypothesis. So let me go scroll in. So you use that to scroll in. That's out just a little bit too much. Let's do this. Okay, so we want to balance it, and in order to do that, we have to actually pull on this and balance it that way. And we want to write that amount down. So 0.86. So that's the first one at 10. Okay, so let me go back to this one. So you would put that under this force in applied to the balance on the left side on the resistance. Okay, so we want to look at arm length 0.5. So like if we put it here, so it automatically goes over. Okay, so we want to look at 0.70. Well, we'll just look at it. So you see to balance it, do you notice to balance it we have to change, do you see how that happens? 0.39. So that's 0.39 newtons of force being used to balance it. Okay, now I'm going to move it over and I want to show you the difference. So if we make the effort side shorter, and we put weight on it, so let me put weight on it. So I put 300 grams and it's at 10 centimeters on the effort side. Let's see how much it takes on the resistance side to get it to balance. So it takes 1.48 newtons. Okay, so but what if we shorten it? If we shorten the effort side. Okay, so now we're at 15. Right about there, I think is balanced. So less effort. It takes less effort. The further we go over, the less effort. You see, now we don't have to do any effort. It already moved it. So that's really what we are trying to show. So we can write our hypothesis. So let's go to our thing, and we can say if the effort side is shorter, we will have a mechanical advantage and do less work. In other words, oh, that needs to be on the next line. In other words, we don't have to put as much effort in, as much force. So less force is needed to move the object. Okay, so the question originally was, how does the lever help to minimize the work needed? Okay, so through observation, we're looking at the lever effort side and the resistance side. To see the relationship. An early observation shows us that there is one. And a mechanical advantage. So just by what we just did, looking at it, putting a weight on there, through our observations and experience, we're able to gauge that. So we want to gather some data so that we can prove it, right? So if we had to write a paper and we had to get the data to show someone else that that's the case, we need to be able to prove it. So let me put these in blue so you can see them. Okay, so we want to put in a force on the resistance side. So force as added, mass to resistance side, grams converted to newtons. Okay, so we that means that we have to pull 2.94 newtons. And we want to put the arm length at 7.70 meters, which is 0.7 centimeters or 70 centimeters. But if we look on here, it only goes up to 60, right? So we have to actually figure that out. And how we do that is by taking the newtons times meters. Okay, so we have 0.70 and we're going to times it by 2.94, and that is going to give us the joules. So let's go ahead and do that. Let me get my calculator up here. Let's see if it'll pull up for me. There it is. Okay. So we want to take 0.70 times 2.94, and that gives us 2.058 joules. 2.058. Okay, and we have significant numbers here. So we have to think about that. And when you look at 0.70 and 2.94, there are three significant numbers. So we need to make sure that we have three significant numbers on in our number. And so we're going to have to round up to 2.06. Okay, so that's that. So then I want you, you'll do this part. Okay, so let me highlight that in yellow. This will be, and you'll multiply that like we just did. So I took 2.94 times 0.70, and it gave us 2.06 joules. So that's how much work occurred. Okay. And then you'll also do this one. Okay. So let's go ahead and fill in this table to start with. So a force in newtons applied to balance the lever with no mass on effort side. No mass on effort side. So we need to go back to here. Let me zoom out. We need to take the mass off. Okay, and with no mass on the effort side, they're saying that it's 0.87 newtons. So pulling force applied to the spring scale when mass is added to the effort. So we need to get the newtons to that. So let's test it out and see. Let's put it back to 0. We want the arm length at 0.5 meters, and the total force with no effort. Actually, I went the wrong way, sorry. There. It needs to go this way. No, I was right. Okay, so it's 0 here. Okay, 0. So it would be the pulling force is 0. So if we do it here, the pulling force for this side at 0.40 or 0.45, that means that we have 45 meters. I did that wrong. So 50, that would actually be 10. Okay. .83. So the total force applied would be 0.83. Oh, sorry, 0.83. So you have to subtract this from the 60 to figure out where to put it. So like 45, you subtract 45 from 60, and that will tell you where to put it. But if we did it at 45, I mean, we can't because we can't go over there. So that's why I'm saying you have to subtract 45 from 60 to figure out where to place it. Ends up being like 10, 15, 20, I believe, 25. And then you'll level it and put the number in there. Okay, so then you're going to take the total force, which is B, and you're going to subtract A from it. So in this case, it's going to be a negative number. Okay, so A is the force in newtons applied to the balance or the lever with no mass on effort. Okay, so pulling force applied to the spring scale when mass is added to the effort. So now let's try it with 300 grams. Okay, so we're gonna add 300 grams. Oops. Put that there, and we need to put it back on 10. And then we're gonna pull it down again. Let me let go of it because I can't see it. Ends up being 722. So this is actually 722. Okay, so now you subtract that amount, 722, and that gives you total force. So we'll use our calculator. 7.22 minus 0.87 equals 6.35. And we did it at arm length of 50. So see, we have 10, between 10 and 20 is 1, 2, 3, 4, 5. So that's 50. Okay, so now we need to take the work times the meter. So that is the 6.35 times 0.5. So 6.35 times 0.5 gives us 3.17. We want significant figures, so we're going to do 3.18 joules. Okay, so let me go back through that. So this number here is when you add the 300 to it. And then you subtract this. So this is what you have to move it. And this is the combined. So if you add mass to it, this is what will have to happen. Okay. So you'll answer for this one, and for this one. Now keep in mind that this means that you're moving it, you're moving the resistance side, okay? But you're adding on the effort side. So that's how you get your numbers. Okay, so let's go ahead and do the pulley lab. Let me go to our other document. Where is it? Right there. Nope. Is this it? No. There we go. Student guide. Wow, couldn't find it. Okay, so we completed the data table. Now we could have done, they do want us to do this, but I kind of bypassed it. So we ended up with completing the data table that was already there. But you could use this data table. It might make more sense to you if you want to. But we complete the data table using the 300 gram mass and varying the fulcrum position as shown. Okay. Explore various combinations of effort, forces, and arm's length so you get a good idea of how that works. And then next we're going to work on the pulley lab. So let's go to that. Can do that by going here. Down to pulleys. Like I said, this was a combined lesson, so all these were in one module. And I'll also provide this link for you as well. Okay. Let's click on that. And we want the student guide for this. I think it is. Back a little bit. Right here. Okay, so it's in your lesson introduction, and then you go to lesson resources, student guide. And that's what we want. So let's move that over here. Okay, and let's do this. Again, your little Adobe thing might pop up and you just have to click on it. But we'll begin the lab. Okay, it says open the Simple Machines Poly Virtual Lab. Do the tutorial. Write a statement setting out the goal of the lab, which we did. Create and complete a table similar to this one. So you want, we're going to test a single fixed position pulley and a single moving pulley and one fixed position pulley with one moving pulley. Now the whole point to Simple Machines is that we want a mechanical advantage. And if you remember in the live lesson that I taught, we showed the students using the different pulley systems to create an advantage. So if they had more than one pulley, a greater distance, a length of rope, they were able to lift their principal. So we're going to see that in here as well. And I'm going to tell you right up front what result we're going to get. So we're going to see that this pulley right here in station 1 is not as efficient as station 3 or station 2. It's not as efficient as station 2. When we see the pulley set up like this, it increases the length of the rope. Same thing with station 3. There's a greater distance length of rope, and it's more efficient because it has the pulley closer to the thing. So let's go ahead and test it. So distance string pulled. So we want to, let's do this one. Now this can be really finicky. I'm just going to tell you that now. And it will be frustrating. Okay, there we go. But you just have to play around with it until you can get it to work right. And let's zoom this in. Let's do it right there. Okay, so they really want us to get this to 40 degrees, I believe. Let me pull up a Word document. Or 40 centimeters, I mean. Weird, it doesn't say that. Huh. Yeah, so the distance the string pulled, we want to actually pull the newtons down to 20 centimeters, or where the thing is at, the weight is at 20 centimeters. Okay, so we want to pull it down 20 centimeters, and we want to look at it. And we can see that at 20 centimeters, there's 2.94 newtons in 20 centimeters. Now, if we pull it all the way up to 40 centimeters, it should say the same thing. 2.94 newtons. Newtons. Okay. So you could even put it at 10, but you want to be able to put it at a point where you can count it. It's 40 centimeters. And then you want to count the dots. So you see how on the string itself there are dots. You want to count those. So on the left hand side there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 dots. So it actually, so you would write that down just on a piece of paper. Okay. We want to write down in distance the amount that we pulled it. So let's measure it. Let's measure it at 35. Okay, so we can say the distance the string pulled in centimeters was 35 centimeters, and that the work applied is 2.94. So you'd put that under force in newtons, which is right here, 2.94. And then you multiply those together. So I can't really write on that, so let me pull up our sheet again. Centimeters pulled, 35. Newtons was 2.94. So then you multiply it. Oh, I'm sorry, distance. I did that on the wrong side, I'm sorry. This goes over here. This is how you pull the string. If we start at 40, how far do we pull it? So if we start at 40 and we pull it to 10, well, to 35. So that gives us, that puts us at about 8 on the bottom. So we would subtract that, gives us like 32. We'll say 32 centimeters. So we pulled the string 32 centimeters. That's what we would calculate. So 32 times 2.94. 94.08 is in joules. So that is the work that was done. The resistance force is this right here. So that's the weight, or newtons, so 300 newtons. So we put that here. And we multiply that by 35. So 300 times 35 centimeters. 300 newtons. I'm so going to scrap this video.